So, we want to do some funky things now, okay? We have done a lot of basics, a lot of simple things, and we want to do something more non-trivial. How many of you have seen color coding?
Color coding.
1, 2, 3, 4, 5. Okay. Are these problems clear? Okay? Okay. How many of you have seen 2 power n algorithm for ham path? This algorithm, I'm not saying color coding, this 2 power n algorithm for ham path using DP. Great. Okay. So today we are going to make some C power n algorithm for Hamilton path, some C power k algorithm for k path, but not the way you have seen it before. That's it. That is a simple thing to say. Okay. Okay, let's see. So we'll worry about what these objects are. I know some of you have seen this in Poland, but you definitely have not seen them into these slides, so they're different. So let me do the classical dynamic programming for Hamiltonian path. Even if you have not seen, let's do a simple exercise. So what is a ham path? You're given this graph and you do a dynamic programming algorithm where your columns are basically 1, 2, 3 up to I, n minus 1 n, and the other vertices. And what do you store here? Basically what you store here is paths of length I ending at Vj. This is what we want to store, right? So what do you want to store? At every here, you want to store all paths of length I, right? All paths of length I ending at Vj. Okay? This is what you want to store. This is what your DP. So clearly, if I'm able to do this in a nice way, so this is my goal. What do we start? Paths of length I, which ends at some particular vertex Vj. This is my goal. Now, so for example, this is one path which you'd like to store. Now, first thing which we learn in DP is that how many paths of length I could be there at Vj? How many paths could be there? Well, it could be roughly n choose I factorial. Okay? It could be that many, right? Because for example, look at a click. Like look at a click. There could be, you take any permutation can realize a path. So if I'm storing paths of length I ending at Vj, I might be storing these many objects. So the first trick which dynamic programming algorithm does is that, okay, if I'm interested in testing whether there exists one Hamiltonian path, we do not need to store so many. We can get rid of this I factorial by in the following way. We say, we keep a subset of vertices who just say there is some way to realize these vertices as a path of length I, right? So rather than storing all the permutation in which these paths are realized, I keep a set which just tells me that, well, there is this set, there is a path of length I starting from somewhere among this which ends at Vj. This is important that you know where you are ending, right? So basically, there could be many paths, but on the same vertex set, but I will only keep one vertex set. Okay? Okay. So that's what I'm saying. As a sets, but not as a sequences. Okay? For example, look, for Vj, there are many. This is one path. This is another path on the same set of vertices, but we are not going to store the order in which it goes, but basically this subset that, okay, there is a path starting at one of these vertices traversing all these guys and ending at Vj. That's it. Right? So basically, we have trimmed our dynamic programming table based on equivalent relationship. We say two vertex sets are same, like two paths are same if the internal vertices they traverse are same. That's it. So what are we storing here? Paths of length I minus 1, which is, what is this? Paths of length I ending at Vj is paths of length I minus 1 ending at U avoiding Vj. But what should be the property of U? U has to be in the neighborhood of this, right? So I can, because we need to do dynamic programming, then how do we do dynamic programming? We say, hey, what is this? Paths of length I ending at Vj is nothing but paths of length I minus 1 ending at U, which is in its neighborhood, and it avoids Vj. Now, if we have this information, we can do this dynamic programming table by first fill this line, then fill this line, then fill this line, and then fill this line, right? Because suppose you want to store all these sets at Vj, you look at its neighbors, look at the sets which are stored, you take out those sets and put Vj, which does not include Vj already, right? This is a normal classical dynamic programming algorithm for Hamiltonian path, right? If you want to store, what do I do? I already have stored this table, right? So I look at those sets. Look at those sets which ends at some neighborhood, pick up those sets which does not contain Vj and include in my family of sets, and that's it. And of course, I include Vj to all of these guys. Is the dynamic programming paradigm clear, algorithm clear to you? To all of you, right? How we will update. Updation is, I have already stored everything up to I minus 1. Now I'm trying to fill this column and I'm trying to fill at Vj. I say, hey, here those sets will be there where the last vertex of I minus 1 ends at U and does not contain Vj. Let's pick those sets, right? So he will go pick out the sets from here, some sets from here, and some sets from here, and get it all sets. So how many stores? Potentially we are storing how many sets? N choose I at any place. And how much time it might need to fill this? At each, you might need time proportional to the neighborhood into this N choose I plus 1. And this is why, how much time this whole algorithm will take? This is the same 2 power n algorithm, right? Because each column can be filled in time proportional to N choose I. Like each column can be filled, right? Because look at here, right? How many sets already stored? N choose I minus 1. You go through each of them. How much time did you take to fill this table? Fill this entry. Sum N choose I. You sum over all N choose I, this is like 2 power n. So of course, I'm not talking about some polynomial factor. So running time of your algorithm is essentially N to something like that, roughly. Because for each entry, you might have to go through list of size N choose I. Basically, it's basically because each time, how many lists of this? You will see as much proportional to its neighborhood. That many sets, and you have to pick out this. So this is why this is roughly like, I may be missing some polynomial factor here, but that's it. Now suppose you wanted to find a path of length k, what will you do? If I'm interested in finding a path of length k using this DP table.
I'll look at the k's column.
That's it. You stop. So I told in the beginning that there is an algorithm which takes n choose k factorial. The classical DP idea allows us to get rid of this k factorial and n choose k. Agree? Okay. And restrict to the first k column, right? So this is how we can check whether there is a path of length at least k or not in a graph in n choose k time. So the worst case running time of this algorithm is going to be O star n choose k. which is like n power k. Now, basically the question is, and this is where we should spend some time and we should think about it, that do we really need to store n choose I sets, right? Why is the running time of this algorithm of this nature? Because at each entry we are storing how many sets? N choose I sets. Okay, so two things to remember. Okay, we want to check whether there exists a path of length k. This is our goal. Okay, and at intermediate level we are storing n choose I sets. N choose I sets. The question is, if we are only interested in finding a path of length I, do I need to store n choose I sets, or we can manage with something smaller, something simpler? You get my question, right? Do we need to store this much, or can we prune this DP table even further? And that is the whole idea of this lecture, is that how and what we need to do, right? Okay, let's try to formalize. You tell me, because now I am not going to tell you. All of you know what DP tables are, right? Now you tell me, what should I need to store here? Okay, some length I, some vertex Vj. We were storing all sets of size I that realizes a path of length I that ends at Vj. All sets of size I. And now I'm telling you, I would like to prune this, right? I would like to store something smaller. What should be the property of that set? Something smaller here I want to store, such that this is a valid dynamic programming table. What do you like to store here? That is a couple of minutes we should think what should be stored here such that we are able to do dynamic programming algorithm nicely. What is an objective of storing this? You tell me, what is an objective of storing this? Why are we storing this? Have you ever thought, why are we storing this?
Well, essentially to be able to compute the value at the lower right corner.
Yes, the reason is, you're very right. So basically that's one thing, but each of them, why are you storing so many of them? Because you don't know the future. Basically what you are trying to store at this point of time is that, well, if there is a path of length k, length n does not matter, these are the, and if that path ith vertex, suppose I'm only looking at those paths where ith vertex is Vj, okay, only those paths. So basically what I'm saying, that if there exists a Hamiltonian path in my graph, or path of length k which passes through Vj, and look at your Hamiltonian path, among all those, look at those which contains Vj, and the first part is I, only those, because we can make equivalency classes based on Vj and this, and that is what this DP table is trying to achieve. Basically what we are saying, that, well, all the Hamiltonian paths probably you can make starting with Vj, probably they could have only these sets as their prefixes. This is all that you are trying to store, right? I do not know what is going to come from the future, but if at all you are able to find a Hamiltonian path, then whatever I am storing here, and if Vj occurs in that path at this place, then whatever you have here, one of these sets can be extended. We can glue them here with this and this. Okay, so let's, whatever we said, let's write them in English, right? Let's write them in English and then just see what we want. So what are we saying? We say, okay, basically, so let's fix length k path. What are we saying? We are saying for all paths of, for all paths of length k, whose prefix has vj at ith place, for all paths of length k whose prefix has vj at ith place, should have one of the sets in my table as prefix. This is exactly what we are trying to store, right? What we are saying that whatever you tell me from the future, this is my vj, I have stored someone who can extend to you, who can work for you. This is all that we are trying to store. Now let's ask many questions to ourselves. So essentially all you are trying to tell me that, look boss, I will give you future, you should give me from your set a prefix which fits and makes a path of length k. It doesn't tell you that you store all of them. It never tells you that you store all of them. All it tells you that I don't know anything about the future, but if you definitely should, because you don't know what will come in the future. You don't, when you are doing this dynamic program, you have no control over future. So here you are storing everything, right? What I am trying to tell you, let's store those guys with the following property. I say, you give me anything, I have someone whom I can match and make a path. Is this enough? What I'm saying, I will not tell you what I store, but I will only guarantee you for all y, for this is my vj, let's call this y. I don't know what, if you give me this y, I have someone here, x, such that x plus y is a path of length k. This is all that I want to store. Is this enough for my dynamic programming table? This is if we are able to understand the motivation of this, right? My trivial DP table stores every possible sets which is possible. Now I'm trying to look, no, I don't want to store. I only want to store some of them. First of all, it may not be even possible, right? But whatever happens, whatever future you give me, I will give you a path which will patch together and it will be a path in this. It means I'm not losing out on anything. For example, what will mean by losing out? So suppose there is a path of length k, there is a path of length k, you gave me this, it says, okay, make this a path of length k starting from here. And every prefix which I find here, right, every prefix which I have somehow intersect or doesn't make a path, then it is a bad thing. Right? Then I have not stored. But this guy will not care even if I have one guy which can patch here, he's fine, okay, I'm able to extend this. This is the whole idea, right? So this is the whole idea. So first thing about this set which we are storing, what should be the property? That whatever you tell me the future, first of all, they should be disjoint. Do I need anything more? Think about it for a minute, right? So now, I gave you some intuition. Now I will try to formalize and let's see if both of this intuition and this matches or not. Okay? So what is our goal? I think we are storing too much for our purpose. If the purpose is that for whatever extender come, I have someone as a prefix, right? So let's call whatever we do not see as future. And whatever we store, we call prefix. Okay? So what is our goal? Our goal is to prove the following. So I want to store F set such that for every future there exists a prefix, for every future y there exists a prefix x such that x plus y, by plus I mean concatenation, is a path of length k. If I'm able to store this, is this good enough? Said, right? So, and of course, I'm looking at only those paths of length k where the prefix is of length I, the ith vertex is vj, because other things will be stored at different entries. This is all there. For every future, I have a prefix which you combine them, it gives you a path.
Well, you actually probably need something different that for any future y that can be extended in the original graph.
So by future, I mean, so this is what I mean. You're right. So by future, up until now, I have been meaning that for which there is already an extender. This is what I mean. For which I already have. By future, I mean, I'm getting these futures by looking at all paths here. Look at this, like all these paths, all paths of length, and take these guys as future. This is what your future is. But you're right. We will make that formal. So basically this is something. So by future, I mean, which is for which there was a prefix. Otherwise, why do I need to store? If this prefix, there is no in the whole big thing, why do I need to keep it? If it is a bad future, it is a bad future. I don't care. But for every good future, I have some prefix stored in me, which they can combine and give me my algorithm. Okay? Is the intuition clear? Is intuition clear? No? Okay. Let's see some slides. Okay. So let P be a path of length k. Okay? This is the most important concept to understand. So please, let's go slow. If you don't, please ask question. Otherwise, you will feel bored. Okay? There may be several paths of length I that latch on to the last k minus 1 vertices of P. For example, so now what I want to say that we're storing, let P be of length k, and for this last part, in my DP table, I just need to store one of the extender, not all the extender. For example, look at this example. Suppose we have path P on 7 vertices, 1, 2, 3, 4, and suppose these are my first 4 vertices and this is last 3 vertices. Now look at this this is our good future because there is a way to extend. Now let's look at this. There are many ways to extend this future, right? One way, another way, another way, another way, right? There are many ways. Do I need to keep all of them? All I'm trying to tell you from that point of time, that for this particular future, which is a good, valid future, I should have one of these extender in my set. This is all that I'm trying to tell, right? Because that's good enough for us to do dynamic programming. That I'm not missing anything, because, I mean, think of this as an adversary. You don't know what they will give you, but you should have answer for everything what future could provide you. So, right? A fixed future and the possibilities for partial solution compatible with this fixed future. This is what it is. And all I'm trying to say, let's try a different example. Okay? Is it I'm going? Okay. So there are, you can also have, if this is your future, this is one way, this is another way, this is another way. I mean, right? So for any possible ending of length k minus I, we want to be sure that we store at least one among the possible many prefixes. This is our goal, right? That for every path of length k, what I'm storing, that look at all paths of length k with this property, for all futures, I have small prefixes. But this could also be n choose k minus I. There are n choose k minus 1, k minus I could be the ending, and for each of them you need to store, what do you call, one each. Not doing good. No? You see what is the problem here? The problem is that it could be that how many future could be? N choose k minus I, last part, and for each of them you have to store one of them. Not good. But still, this might be a better idea, because n choose k by 2. What is the worst case you will be storing here? When it is exactly equal, it is n choose k by 2. So it is, even if we are able to do this nicely, carefully, we might be able to do better because n choose I equal to n choose k minus I. So the worst case of this will happen over k by 2. So we might still be able to do slightly better, but that's not the goal. We will not achieve much from here. The hope for saving comes from the fact that a single path of length I is potentially capable of being a prefix to several distinct endings. This is our goal. What we are hoping to achieve, that for many paths of length k minus I, there is one guy who is able to take care of it. That is our hope, that is our goal. Is it possible when, for example, let's look at this example. This is one ending, this is one ending, this is one ending. But the same path is able to take care of all of them, right? Right? So for example, if I would have stored these paths, then if you would have given me this future, it adds. If you would have given me this future, it still adds. It is given me this future, it still adds. Now, so basically, let's abstract out whatever we are saying. What are our partial solutions? Paths of length j ending at vi. This is what people are storing here. All paths of length, all sets, blah. What we want? A small representative family. And what do we want to achieve from here? Let's see. If you have a path of length k where vi is the ith this is the first j vertex, it ends at vi, and this is k minus j, then clearly this guy appears in the partial solution. Then what do we want to achieve? Then there exists some prefix in my small representative family that such a thing exists. So this is what symmetrically everything is. That if I have a path of length k, look at all partial solution, which is the big box. What I want to store is something smaller with the property that, well, if this plus this gives me a path, then there's someone else in my representative family which combined with your future will give me a path of length k. This is our goal. Is this correct? I mean, are you happy with this if this is what we will store at DP table? All I have tried to tell you up until now, that whatever we are storing at DP table, basically we could think of storing this information. And now we will tell you how to reformulate and everything, but this is what we would like to do. Would this be enough to do our dynamic programming? So when you do now, what you say, okay, this is a set, among them whichever can extend, and you try to do DP over that. Okay, now, so basically we would like to store at least one path of length j that serves the same purpose. So what do we have a question? So we have been given a big family F of p size subset of n. Now think of these sets which we are storing as some p size set, S1 to St. What do we want? A small subfamily f hat of f. I will tell you what I mean by this, such that for any x subset of n of size k minus p, if there is a set S in F, we would like to do this, such that x intersection S is phi, then there is a set S hat in F hat, such that x intersection S hat is phi. It's just a mathematical question. What I want, you are given a big family with S1 to St, each of them has size p, and what I want, if I want a small subfamily F hat of F, such that for any x subset of n of size k minus p, if I have some set whose intersection with this is empty, then there is some set S hat in my this whose x intersection S hat is empty. This is what I want to store. Now, second half of a solution can be any subset. This is why I am not demanding anything. I said, okay, I do not care. I said, so now think of this, what it tells you. It tells you this will be my family. So in terms of path, let's see if okay. So we say that, look, I don't know about valid and all this. Okay, let's make our question slightly more easier, interesting. Okay. This is everything. This is your sets. What is this? S1, S2, St stored here. Right? What is the property? Blah. What it says that what do I have is that what I want to find is that now I'm trying to abstract out this problem. So think of this of size I. So this is I, everyone has size I. What I want to find here, a small thing inside this set F with the following property, that for every y subset of n, cardinality of y k minus I, or k minus p, let's call them p, just to be of size p, doesn't matter. If x union y, sorry, x intersection y, if there exists x here, so x intersection y is empty set, implies there exists x prime here, whose intersection with y is empty set. Okay? If I'm able to do this, and this is a small, I'm great. Why? Look at your k minus p, last ending of the path. This is what you gave me y. Your future. You say, hey, look, here is my vj plus 1, blah, 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 some vk, right? Some last patch. Clearly, I have someone here, x intersection this is empty, prefix in this is empty. I tell you that this has someone x prime, whose intersection with your future is empty. Now, why does this imply it's the path? If I'm going to keep object from this, what is the property of this? What is the property of this? Is that, look, now last vertex here, so I have to do this with respect to path. So path is vj here and the remaining here. So because it is a path, there is an edge here. Already there is an edge here, vj and your y. Now you have someone here, what is that? A that is disjoint from here, and there is a path which ends at vj. This is why, because every path here has a property, every set here has a property that there exists a path of length p which traverses them somehow and ends at vj. Every path has this property. So just by making them they are disjoint, and because we are storing a subset of family of this guy, it tells me that if you had a path before, I have a path now. Right? This is how I want to use these sets, right? So all I have done is that I have to find this object, a small object, with respect to a particular family, right? This is all. Now, why their path and this is taken care by the kind of family we start from. Because we have started with a family, what is extra property we know about? Well, all these sets are actually, they are realized some path of length p ending at vj. This is guaranteed. If this is guaranteed and this is disjoint because of this theorem, then I combine this, I get a path of length. Okay, right? So I have abstracted out a problem about these sets, problem about this family, to literally a combinatorial problem. What is my combinatorial problem? I give you sets S1 to ST family. Forget it now. Forget what its connection with K path is. If you could not find a connection, just think it's a combinatorics problem. I give you sets S1 to ST. And what is my goal? I want to find a small subfamily f hat of f with this property, that if there was in the big family someone is disjoint, then in my small subfamily someone is disjoint. That is my goal. Okay? Is this abstract problem clear? So basically,
but it's stronger than we need.
Yes, it is very stronger than we need. And it seems if we do not want that stronger, we can do great. Also, we can do slightly better than what I will try to show you. Okay? So this is what I mean. The second half of solution can be any subset. And basically what it means, if there's a set S in F such that X intersect, so this is basically a valid patch, our prefix, then this S hat is a guaranteed replacement. Now, big is at most n choose p. If universe has size 1 to n, then this family could be as big as n choose p. I don't know. And what I mean by, so what Bolovas proved in 1965, that actually there is a set of size k choose p among them which does this job for you. So if you give me S1 to ST, however large the sets are, I will give you, there is a small set inside this family of size at most k choose p, at most p. So basically this, what you need to store inside only depends on what is my size and what is the future. It does not depend on the universe size. Now, so there are 2-3 questions. So this is what I mean by small. If A, first of all, is it clear to you why they exist? No. That's one thing. And even if they exist, there are many more questions. How do we find them? Second question. Third, how do we use them in algorithm? Right? But it seems that if we are able to understand this basic combinatorial question, we will be able to use them as a tool in our algorithms. Right? So that is the goal. So this is where you will see where the matroid comes. Matroid comes because how do we find these sets? Right? I give you big family, how do we find them? There are more issues, we will get to that, how to do dynamic programming and blah, blah, blah. But how much time do I have before we can take break? 5 minutes?
Like 15 minutes.
Oh, we have 15 minutes, that's great. So let's do one thing. Let's prove this. Existential proof. I'm not going to give you construction. And trust me, all of you know this proof. All of you. I mean, I will not use some amazing, this combinatorics, this, nothing. Very simple two-liner. I will not be able to prove K choose P to you, but something very close to that. Okay? Let's prove this. Just combinatorics, let's try to prove it. Isn't it really this thing that isn't it a curious statement? Okay. Okay. Let f hat the subset of f be a minimal family, okay, that achieves this. You know what is a minimal family? So basically I delete. I mean, there's no redundancy. So suppose f hat is some a1, a2, al. Why it is minimal? Let's try to say by definition. I say this is minimal. Why are you keeping a1? Because there exists some b1, such that I put it here, such that a1 intersection b1 is empty set, and for all j greater than or equal to 2, aj intersection b1 is not equal to empty set. This is the definition of minimal. Like what I'm saying, that if a1, a1 has a private set which it is disjoint with and others are not disjoint with. Otherwise, what is the point of minimal? I mean, if every set which a1 could take, other people could take care, delete a1. You see what I'm saying? Look, what I'm saying, suppose I keep a1. a1 is disjoint from many sets. Many sets, a1 is disjoint. Now, for each set, if I find someone else who is disjoint, then keeping a1 is useless, right? Our goal is that for every future of y of size k minus p, if someone is disjoint here, I should keep someone. Now, what is the role of a1? If it is a minimal family, then by definition, a1 is able to take care of some set which other people are not. And what is the meaning of that? Is that there exists b1, so the a1 intersection b1 is empty set, and for all j greater than or equal to 2, aj intersection b1 is not empty. No one else is able to take care of this set. Similarly, there will be b2 here. Similarly, there will be bl here. Agreed? So what do we get? We get ai intersection bj equal to empty set if and only if I equal to j. Right? So if, look at any f hat which is subset of f, and it's the minimal. I'm not any minimal family, any, not even minimum, any minimal family has a property that for each ai I can find bi. And what is the size of bi? Each bi? So each ai has size equal to p, and each bi has size equal to q, because this is what we are trying to compute representative for. Is this clear? Is this to everyone, that let f hat be a minimal family of f, then for each one in my minimal family I have some bi of size q which he is disjoint with but others intersect. This is a combinatorial statement.
So q is k minus p.
Q will be k minus p in our setting, right? So now I'm going to show L is bounded by something. Then we will be happy. For example, if we could show that L is at most k choose p, we are happy. If I can show L is at most k choose p, then I'm happy, right? I said, okay, compute any minimal family which achieves this object. That's good enough for you. Any minimal family. And that's important, because minimum and all, we don't even know how to compute, right? But here, at least minimal gives us some control over how to get. Any minimal family has this property, that the number of sets is bounded by k choose p. Okay, it will take me some time to prove k choose p. It's not very hard. Let's do something even simpler. Okay, let me prove to you that L is at most 2 power k, always. This is an easy proof. Okay, so what is my proof? Let's see. Okay, so imagine that you have a universe v1 to vn. Okay, you have this universe from where these sets are selected. These ai's, bi's are over some universe, right? Now I'm going to call a partition. Okay, so universe is partitioned into u1, u2. u1, u2. Okay, universe is partitioned into u1, u2. I'm going to call a partition, or a partition u1, u2 is good for some pair ai, bi if ai is contained inside u1 and bi is contained inside u2. This is it. I'm saying that look at a partition of my universe into 2 parts. I'm going to say that this part is good for particular pair ai, bi. If ai is completely contained here and bi is completely contained here, then this is good. Okay, very nice. Okay, so let's gi be the partition which is good for ai, comma bi. Okay, so there could be many partitions which could be good for ai, comma bi. Agreed? So I make those partitions. Okay, now comes the beautiful claim. This gi intersection gj for I not equal to j is empty. Okay, so what I'm claiming, gi intersection, let's call this gi intersection gj is equal to empty set if I not equal to j. I said, what I said, this is a very simple statement. I said, look at the people which are good for some ai, bi, this is like gi, and some people could be good for gj, like for aj, bj, but the partition which is good for ai, bi is not good for aj, bj. Why? Let's prove this. This is very obvious. Suppose, look at zi. It is good for ai, bi. Can it be good for aj and bj? Okay. First of all, aj has to be disjoint from bj. So where bj has to go? bj will also be here, but bj has to intersect ai. But ai is completely here. So same part cannot be good for 2 pairs. Do you agree to this? Right? What I said? GI intersection GJ is empty. So suppose I started with a partition which is good for AI, BI. Suppose this is, it means AI is here, BI is completely here. Now suppose it is also good for AJ, BJ. Yes?
Pairs are ordered.
Yeah, suppose they are ordered. It doesn't matter. Suppose they are ordered. E1 is ordered, E2 is ordered. So that will mean 2 power n plus 1, right? 2 power n plus 1. Okay. So is this clear? Right? That because AJ has to go here, BJ has to go here, then how AI will intersect BJ? Because AI intersection BJ is empty set if and only if I equal to J. Not possible. Great. Okay? We are done now. Let's count. Summation Zi, I going from 1 to L is less than equal to how much? 2 power n plus 1 because it's ordered partition. Is this correct? Because each partition is counted only in one set. So it's possible that some partition may not be good for any pair, but if some partition is good, it is good for only one pair, right? So this is why this is correct. Now what is the lower bound on this? Can you say how much at least this is? Well, you fix AI in one side, fix BJ in other side, and you do not care where others are. Any partition of them is good, right? If I fix AI in one side, BJ in other side, any other partition is good for other. So basically this is greater than 2 minus n minus k plus 1. Agreed? Mm-hmm. Then we are done. So this formula becomes L times, at least this is L times 2 minus n minus k plus 1, which implies L is at most, okay. No magic. Is this proof clear? I mean, we didn't use any big computer science or combinatorics. Okay?
So if f is given explicitly, then this is...
You just compute a minimal family,
right,
and you are guaranteed by this theorem that it is small. Right? Okay, now how do you get K choose P? This is also not very hard. What you do, you look at this universe, V1 to Vn, okay? You say, you make a permutation of that. Okay? You fix a permutation of V1 to Vn, and you say that this permutation is good for a pair if all the vertices occurring in AI occurs before any vertices in BI occurs. Okay? And you can show that the same permutation is good for only one pair, and then you do this kind of computation, and whatever you get is K choose P. So I just give you a slightly simpler proof because it's slightly easier. Otherwise here I have to take 1 by P factorial blah blah blah, but this is how the proof is. For the permutation, you define what is good for a permutation of universe. AI comes, like all the elements in AI comes before all the elements in BI, and that's it. Now same permutation cannot be good for two people because AI and AJ, if you think AI BI. Now look at AJ. AJ has to occur, like look at BJ, look at AJ. AJ has to intersect BI. AJ has to intersect BI. So the poor guy has to come somewhere here. Now if AJ comes here, all the elements of BJ can only go after this, but then it will not intersect AI. So you do this and then you get this. This is proof by Luby and all these people. It is by this permutation proof. And
so this is not the original proof.
This is not the original proof. Okay, so 2 questions. Now before we go for lunch, I think this is a great time to break for lunch. Please think about it. How do we find these sets? Right? And how do we use it in a nice way? I think that is what I will concentrate.
Finding this subfamily is easy if the initial family is given to us explicitly.
Yes, but how can we find like easily? Yes, it is easy to find, but how can we find what I mean much more efficiently? Okay, there's a matroid definition. So I will not go to this. Yeah. How do you find these sets more or less proportional to the output size and input size, like linear, almost linear? It's very hard. And that is what gives you the fastest known deterministic algorithms, because you need to compute them much more efficiently. Like otherwise your algorithm could take, look, why it is easy? Why do you say that it is easy to, even if I give you this S1 to ST, why do you say that it is easy to compute this family?
Well, we just go over the sets one by one
and do what?
Okay. I see.
You have to find a set which is disjoint from him, intersect all of them. Then only you have to keep them, right?
Right.
So there's not easy, right? If I have to make this, so I want to keep first set. Do I keep it? Why should I keep it? I should keep it if there is some set which it is disjoint with, and there are many such sets, and one of those sets should intersect all of them. Then only I'm going to keep this. Otherwise, there's no point, right? And that's a hard job, because future you don't see. So if you are looking for n choose p into t algorithm, then that's okay. But we'll come back and we'll make one trivial algorithm and one non-trivial algorithm. So what is our objective? I give you this f, and I want to compute this f hat. Let's stay with this combinatorial problem, and once we have found some algorithm for this problem, we will see how to use it for the algorithm, and then we'll come back and do a slightly efficient constructions. Okay, so all of you agree that and now if I tell you that you know also how to construct this, would you believe me? All of you know how to construct these AIs. Okay.
So
You know how to construct f hat having f
yes.
Efficiently.
Yes. So let's look at the brute force idea, and then we will try to make it more efficient. Okay. So let's assume that you are given this S1, S2, ST, right? And what is the goal? Each SI has size P, okay? And we would like to get f hat subset of f of size k choose p, which is interesting for us, right? Now, as I told you, what we will try to do is to find a minimal f hat. That's our goal. And the moment we are able to find minimal f hat, the size bound is guaranteed by the proof of the theorem. Agree? Okay. Now, first question. Why? So I have S1 in my hand, okay? And I ask myself, why should I include S1 in f hat? Why should I include S1 in my f hat? So my answer is very simple. I say, okay, if there exists a set Y such that mod Y is Q, S1 intersection Y is empty set, and Sj intersection Y is not equal to empty set J, then I must keep S1 in my family, right? This is what I want to test. And as Sasa told us before, one idea could be that we guess this Y and check whether, so we guess this Y and we check whether this property is satisfied or not. How? We guess Y and check whether it is disjoint or not, and then whether it hits or not. Now that algorithm will take n choose q or n minus s1 because you want to be disjoint, so you only enumerate all y's which does not intersect y, so that we can save on some things. And for each, I have to go through each sets to check whether it intersects or not. So in this much running time, I can definitely find, right? So in this much time, we can identify whether S1 is important for us or not. Agree? So for each S1, this is going to take time this much. So the overall running time of this algorithm is going to be multiplied by t, because you have to do for S1, then for S2, and this is the way we can find this algorithm. Agreed? Now, we want to find an algorithm. This is ugly algorithm. I'm okay depending on t in some polynomial way, but I'm not okay depending on the universe size in a polynomial way. So I would like to make this algorithm an improved algorithm. Okay? Goal, improved algorithm. Okay, and my answer to all of you is, you know this algorithm. All I have to do is that I have to do same algorithm. I have to just analyze it correctly. Okay. What is this y look like? What is this y? What is the nature of y? It hits all the sets S2 to ST. Agreed? Y intersects every S2 to ST. Agreed? It means I can have a branching algorithm. Right? I'm trying to find such a y exists because all I'm interested in is finding a y with this property. That's all that I'm trying to do. So what I say, okay, look at S2. I say, this is the first algorithm we made, vertex cover. Okay, I'm just trying to find this y. I look at S2. S2 minus S1. I look at the set S2 minus S1. The y which I'm going to construct must contain one of the vertex of S2 minus S1. It must contain, right, one of the elements of S2. The y which I'm going to construct, it intersects every one, right? So I branch over. So for now, let's assume that each of S2 is disjoint from S1. It doesn't matter, just for simplicity. Now I branch on each element. Is this the y? Does this y contain this element, this element, this element, or this element? And now, now I have a set family. In the beginning, I was trying to find my S minus S1. This is my current family with parameter q, right? I'm trying to find an y which is disjoint and blah. Now what I do in this branch, at this branch I decide, okay, this element, so suppose S2 is, suppose A1, A2, AP, P element. I say, is this y which I'm trying to construct contains A1, okay? Now what I do some S star, comma, Q minus 1. And what is S star? You remove all the sets which intersect A1. In the second branch, let's call it S2 star minus Q minus 1, and here I remove all the sets which intersects A2 and dot 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 AP. So it's a P-way branching. Now here, now I pick up another set which needs to be intersected by y, I branch. But notice each time my Q drops by 1. So and what is the branching? It's basically T of Q is less than equal to P times T Q minus 1. So this algorithm actually runs in time P power Q. So in P power Q time, I can find if such a y exists or not. So it doesn't need this much running time. All it needs is P power Q. Right? Right? So basically, to make it disjoint, you only branch over those elements of S which does not intersect with S1. That's it. It will only make your algorithm better. It will not make your algorithm worse. If I'm able to find such a y, you can always assume that the number of elements in the universe is at least p plus q. Then you take this, which you have found, which intersects everyone, you just make it large that it becomes q. What is the property? S1 intersection this is non-empty, and it intersects all my sets. Now, because of this, I must keep this S1, right? And if this algorithm fails to find any y, it means this set is irrelevant for us. You delete it. You do not put into your this thing. So this is the way to find a minimal family, right? So I take each Si. Now I try to find, is there a y which is disjoint from him and intersects all this? This is nothing but a hitting set for this of size at most k. So this gives me an algorithm of running time how much, right? For each, so this algorithm will run in time p power q into t square. It is independent of universe size. Okay, is everyone on board with this algorithm? Because I actually did not try to do any very fancy stuff yet. So if I give you a family in this much running time, I can find this f hat which is minimal, and my theorem tells me that whatever you have got has size k choose p. That's it. Please ask question, because I mean it's not very hard. At least we should understand the basic minimum of any talk, lecture. The rest we can forget. So for me this is a basic core, because it is not relying on too much. I have characterized what minimal family means, and for that minimal family we need to do something. Okay? This is good enough for us to give an FPT algorithm for k path, and this is what I want to tell you, and then later on I will tell you how we can do it even better. If we can find these things, at least I will give you one algorithm today who will find this in p plus q choose p, omega minus 1, I think t or something, which is very efficient. In fact, what you can do actually is basically p plus q choose p plus q divided by p, some p into t. So something of this nature. So like there are many fast implementation of this, which gives you very fast algorithm for these problems. Okay, so we will not go into this, but we will definitely see this algorithm today. Okay, but it may be slightly hard to keep in head, but here is one way to construct these sets. So look, I mean, how much smarter we have been just because, and this was the best algorithm known till 2013. We didn't know anything better than this. I mean, this obvious implementation was the only known algorithm for this problem, and it was first given by Monin in 1981 for k-path algorithm. This is the algorithm. So his algorithm is actually using representative sets, and this is how he constructs. Then, but his algorithm took a little bit more time. Then Daniel Marks gave an algorithm for this problem when he was doing dynamic programming in 2005, 2006, slightly faster algorithm and some better parameters, but we didn't know. And luckily, let me tell you, so the people who use in kernelization algorithm, okay, they use this algorithm for q constant.
For q constant.
Like they apply this algorithm for q equal to 2, q equal to 3, q equal to 4, and hence even this algorithm, which I just now told you, is okay for them, because p power some constant is still polynomial. For kernelization purposes, we need it to be polynomial time algorithm. So even this algorithm, if you notice, is for fixed q, it is polynomial actually. So you gave me a large set, right? I can give you a small set in actually, of course, polynomial in the input size in this, right? So, and this is how kernelization is used. So for kernelization purposes, it is okay to even have this basic algorithm for at least this version. Okay. So now let's use it to make algorithms. That's all that I want to do now. Okay? Because now I have given you everything. I have defined what depth sets are. I gave you one algorithm how to construct it. Now let's see how to use it. I mean, what can we do with this, right? And then later we will, towards the end of this lecture, we'll try to give a faster algorithm for this purpose. Okay? So even if you are lost, it's a good time to be fresh, because now we are just going to make an algorithm. And it's nice dynamic programming algorithm, because there are lots of issues, right? If I'm trying to use this, I have to construct what is this f? What is this f hat? How do I get this f? There are lots of issues which we need to handle it. Okay. So let's prove two little theorems, okay? Just to show. Okay, so now I will rub this, okay? So please see the definition and see if it fits. Generally in normal lecture we just gloss over these little tiny details, which I'm not trying to do today. Okay, so suppose I have some f, okay, f, and I'm going to, by f hat, if I do this notation, rep q, it means f hat is a q representative of f. Like for q size future, it satisfies all this property. Okay, so this is a symbol. F hat, this is called q representative of f. Okay. Now suppose I have f1, and someone told me that it is q representative of f. First fact. Second fact, f2 is a q representative of f1. Then I tell you that actually f2 is also a q representative of f. Like that, this is transitive, right? Why? Let's see a very simple proof. What it means. What is the meaning of f1? So suppose I have some y for which, so this is first f, there is x here, so that x intersection y is empty set, right? What does this tells us? What does this tells us? There exists some x1 in f1 such that x1 intersection y is empty set. Agreed? x1 intersection y is empty set. Right? Now, what does this mean? That f2 is a q representative of this. Anything for which x1, anything for which now f2 is a q representative of, this is what I need to show, right? So I need to show that if I give you y, which is blah blah disjoint here, there is someone here who is blah blah disjoint here. Now, what we know, x1 is in f2, right? This implies there exists someone in f2, say call it x2, whose intersection y is also phi.
Could you remind me this? Q is the size of x?
No, cardinality of y is q. Okay? This is what meaning of q representative is. So what I say is that suppose there exists x in f so that x intersection y is phi. What does the first implies? First implies there exists some set x1. Okay, let's write it simply. There exists x1 in f1 such that x1 intersection y is phi. This is by definition of rep sets. Now I want to say, okay. Now what we know, what we also know, now we also know that f2 is a q representative of f1. So basically what I'm saying that I'm trying to find someone in f2 who is disjoint to y. Now what I say, okay, look, what we know, x1 is in f1 and x1 intersection y is phi. Now f2 is a q representative of f1. So apply this inequality. It means there exists x2 in f2 such that x2 intersection y is phi. No? Okay. Okay, all of you look confused.
What does mean Q representative of some family? Because family is Q representative independent.
So when I say that f hat is a q representative of f, if there's a set S in f so that x intersection S is empty set, implies there's a set S hat in this, so this happens. So it represents all Q size sets or Q size future. Okay, this is all that. So, okay, let's write it more formally. Okay, if oh, thank you very much. Let's see if black. Tell me which works better. Okay. Is this work better?
Yes.
This both are fine? Okay. So what is the meaning of Q representative? Okay. So basically this F hat is called Q representative. Okay. F hat subset of F. I'm going to call why Q because it is good for Q size set. So for example, basically what I want to say, if there is a set S in F hat, okay, now for any X subset of n minus n of size Q, this is what the future is of size Q. If there is a set S in F such that X intersection S intersection X is empty set, implies there is a set S hat in F hat such that S hat intersection X is equal to empty set. This is the definition. Basically future is of size Q, then I'm going to call. This is just basically the same definition. Now what I'm saying here, this is transitive. Why? I think that maybe picture will be best. This is my F. This is my F1 and this is my F2. Okay? What it says to you that if there exists some X outside such that S intersection X is empty set, S intersection X is empty set, then there exists some S hat such that S hat intersection X is empty set by definition. Right? Now what we know extra, forget F1. Now what does this mean? If someone in F2 is disjoint with X, then there is someone in me who is disjoint than this. Right? So it's 2 hat here. This is all that I'm trying to tell you. So what I'm saying that if this property of someone disjoint here with someone is maintained here, then if I find representative of even this set, it is going to work. So it is transitive relationship. This is all that I'm trying to say. And why? Because if this is what I try to say here. Now if you see, this is 2. Now I want to show that, okay, so let's see. So you give me X, and what is the size of X? Which is Q. And what is our first assumption? That there is someone in F who is disjoint from them. So what is that? Suppose there exists S, so that S intersection X is equal to empty set.
So is it the same X? Should it be of size P or?
No, X is future. S is of size P. There exists S in F.
Oh, I mean.
This is like K minus P. This is why.
No. Here X is future on the slides. X is future, right? And
yeah, this is why I'm trying to stick with that slide definition. Okay, let me rub this. Okay, maybe I'm confusing you guys. Sorry. Okay. Let X of this of size K. Okay, such that what we know, there exists S in F1, sorry, S in F such that X intersection S is empty set. Agreed? This is what is starting. Now what does the first inequality means? It says that look, F1 is Q representative of F. First implies there exists, say, S1 hat in F1 such that X intersection S1 is empty set. Agreed? This is fine? Is this fine? This is just the definition of this. But what I want to find is someone in F2 which is disjoint than X. Now, what is the meaning of this? F2 is the Q representative of F1. What is the meaning of this? Anything which is from the future. So for example, you take your X such that there is some set which is disjoint in F1 from this. In our setting, this is S1 hat, right? S1 hat intersection X is phi because of this. What does it mean? It means F2 is a representative of this. It means if something is disjoint here, then I can find something here which is disjoint. So this is why I say this implies there exists S2 hat in F2 such that S2 hat intersection X is equal to phi. This is all that I'm trying to say. So what I'm trying to tell you that, look, if I think the best, so this is basically what I'm saying, this is what happens. If suppose F1 is Q representative, F2 is the Q representative of F1, which is the Q representative of F, then this implies that F2 is a Q representative of F. This is all that what I'm trying to prove, right? And for that, what I'm trying to, this is all that I'm trying to show, right? What I'm saying is, if there is someone here which is, so you fix your X. This is your fixed future, right? And suppose someone is disjoint in F. I want to find someone disjoint in F2. This is all that I'm saying. I'm trying to find, suppose there is X, and such that what we know, there is S in F, so that S intersection X is empty. This is given to me. This is my starting assumption. I want to tell you that in fact, I also have some set in F2 which is disjoint than X. And what I say, okay, because of this definition, I will find someone in F1 who is disjoint than this. Now, what is the definition of this? This tells me that, oh, if someone is disjoint here, then I have someone who is disjoint inside this. So to apply F2, you first need to find a set in F1 who is disjoint than X. That's all that it is. So you apply the definition twice. It is not more than that. I mean, it is not magic, or it is, I don't know, maybe I'm not saying in the correct way that you look confused, but if you look at this for a few minutes yourself, I think probably it will make more sense. So I'll let you think for 2 minutes and I'll stop speaking.
I think this explanation was completely clear.
But still, I mean, please convince yourself, because it is just applying definition. It is, I mean, if it had been some more wise thing, then I would try to explain to you, but it is really not a wise thing. Right? It is just transitive. Like, it's basically, I actually look at this picture. Look, I have X, F1, F2, F1, F2. This is how because by inclusion, S and X, someone disjoint. It means I have someone here which is disjoint by definition. And what this tells you, if someone disjoint, then someone disjoint. So I have S2. This is, I mean, for me, this is all that it is. Like, first, this definition implies if this, then this. Now you apply definition to this, and this implies this. This is it. So this is all that I'm doing. It is transitive. Now, why it is important, I'll tell you in a minute why it is very important that this is transitive. Because, remember, we are trying to do dynamic programming for K-path, and we are supposed to keep things representative for a huge set whose size is unbounded. All right? If I explicitly give you the set, how will you make an FPT algorithm then? If I have to explicitly give you this set and you reduce, you are dead. So somehow we have to do this dynamic programming in a very, very smart way, right? Very, very smart way. And this is what it is. So it's just a normal dynamic programming trick. So I think it will be useful in many other settings, like the trick itself. Okay, this is dead. So you forget it, don't worry. Please do not worry about matroid. So, okay, this is independent, no. Back to Y. Okay? So we are back to K-path. We have done a lot of detour. We defined something.
Check this. Probably it is just kind of, yeah.
Oh. Okay, let me sit for a minute. Okay, now we don't need, we are all there. Okay, worst case running time is n choose k. right? And representative set computation gives me small thing. This is what we told. But look at the best running time which I told you. It's still, if I remember correctly, it was, let's just write it for our sake. It was branching factor p, size q. So p to the power q, the t square, right? This is what it was. T was the size of the family. Okay? T, size of the family. Okay, so this is very clear that if I give him this big family, it does some computation, but and returns me something small. That's great. But what should I give him? If I give him n choose case size object, I mean, it's not going to give me anything better. T square is sitting here. So we need to be more smarter than this. This is all that I'm trying to tell you. So not so fast. It's too big. It's too big for our algorithm. Like, it cannot handle. Okay. Now I want to use this fact in a smart way. Okay. Right? So what we do? Let's please stop me if you don't understand this algorithm. Because you can understand this algorithm even assuming everything as a black box. Okay? Now look at the first guy. What are you trying to store here? Like all paths, what we were storing here? All paths of length 1 which ends at Vj. How many such paths can be there? How many paths? As much as its neighborhood? Like all paths of length. If you count as edge or something. But what we know? There is a set of size how much? K choose 1. So now our family has size, I mean this is bit. I think if we use vertices, okay, so let's assume that we are only using vertex, then this is basically singletons. So there's nothing much to do here. Okay, so what is an idea of our algorithm? Let's try to understand this algorithm a little bit.
Do you tell once again what is K choose 1? K choose 1 is the size.
So now we have to try to do this computation, right? So this is why. So let's write down our f hat. What is f? What is f we are trying to construct, right? Let's write down them.
Just for the first column.
This n is upper bound of the number of
Entries. Okay. So what do I want to keep? If you remember this table, so what is f? So let's make table which is at I and Vj. So what we were trying to keep? We were trying to keep a set X, or let's call it some set S, okay, set S with the property that there exists a path of length I ending at Vj. Agreed? This is what our object is. Now this I is the size of the set. So F1 Vj is actually equal to Vj itself. Agreed? This is all that it is. Right? Okay. Now I don't know why it is written and maybe I made a mistake. But so we have to do nothing. So now what are you trying to say?
So what is here? I is equal to 1? You mean
Sorry, not I, 1. So like singleton, right? So this is fine, single vertex. So we are thinking of vertices as this. And what it means that what we would like to do, we would like to, for this, we would like to compute, I mean, like in retrospect, I want to compute what? F1 Vj hat, and I want to compute its representative. What representative? You tell me, what representative? k minus 1. Because future size is k minus 1, guys. Right? So what I'm saying, anything which is of size k minus 1 from the future, I should have someone who's, if this set has someone disjoint with respect to some set of size k minus 1, then I should have some element which is disjoint from that. Okay? And what does our algorithm will do at this point of time? What is p is 1, what is q is k minus 1, and what is t square? So I will do this computation. So I keep this small object. So at any point of time, I will never keep anything but representative. This is what I will keep every time in my dynamic programming table. This is my goal. Okay? Now, so that it never happens, something nice. Now let's look at 2. So now let's think what it is trying to do and what we will try to do. Okay?
Second. I still don't understand what is this k choose 1.
It is.
Is it this representative family?
What is the size of this? What is p here? 1. What is q here? K minus 1. And what is p? Is 1. So what is the size of this? Size of this is p. Size of this, if you remember, it was k choose p.
Okay.
Which is basically k minus 1. Okay? So basically this is size is k choose p always. Right? What is p here? 1.
Right.
So this is basically equal to k choose 1.
Right.
Right? The size of this family is, what did we say? We say then there is a family of size k choose p. So k choose p. P is 1 for us.
Right. So in this particular case, the representative family is larger than the initial.
Yeah, but you will never, because it's a subfamily of this. So you're only going to return 1. It's okay. Look, what is it? It is a subset. You are not, this is a subset of this. Your representative family is a subset. This is what our algorithm did. You gave him fix this, check this. Fix this, check this. So what it finds you is a subfamily of your given family. So if it is 1, it will just return you that. It will do nothing. Right? What did our algorithm did? If you remember, if you had set S1, S2, ST, by definition, this representative is a subfamily of your family.
Exactly.
I am not computing anything from outside. Right. Otherwise, you will make mistake. Lots of mistake. Right? And what did it do? It fixed one set and tried to check, do I need to keep him by doing this? If you need it, then you removed it. So basically what you are finding is a subfamily of your given family.
Yes.
Okay. Okay. Now, so you have computed the first row. Now I want to compute the second row. How I say? I say, look. Very nice, very nice. Now, what is the role of this objects? Let's try to understand what is the role of this object. So basically it tells you, look at any future. This is any future, and what it tells me is whatever little you have stored, I can use these blue guys as the first element. Or whatever sets you have chosen, I can use one of these sets for doing as a prefix. This is all that we have proved. Now I want to do for the second. What I say, I said, okay. What I will do, I said, okay. So for now, let's do it for suppose somehow we did it. Then we will see. Okay, so we have done it for some I stage. Okay, let's do how we will do I plus 1 stage, and that's all that I'm trying to tell you. Now what we do at ith stage, what is this? At this stage, this is where the clever part of what you are computing comes in. Okay, so this is what representative we want to find for this family, but this is very big family. What do I have? I have the following thing. This is my I minus 1th entry here. Okay, what I'm keeping here for some Vj, what I'm keeping here? I'm keeping here f I minus 1 Vj hat, and what was the representative size? Please tell me. It was this. I think I was using rep. Okay. What it was? K minus I minus 1 of what set? This. This is what I have stored here. After I minus 1 stage, here, this set is stored here. Right? And what is my goal in the next stage? To compute a representative of this. So what I do at this point of time, I don't compute this first. I first compute something intermediate. Okay? What I say, what do you mean by intermediate? I say, look, okay, so at this point, suppose I'm trying to compute some Fi Vj. This is my Vj. I want to compute this. Now, what I try to do is very obvious trick. There's nothing fancy happening. What you do is that, okay, how can someone reach me? How can someone reach me? Someone can reach me by reaching my neighbor, and using me as an edge. So what I do, I make some stupid family first. Okay, let's call it F1 stupid. Okay, I will tell you why I call it stupid. I say, look, whatever you have computed in this table, for my neighbors, V in neighbor of Vj, F hat I minus 1 V. Take this union. Okay, this is what I did. F1 stupid is this. So whatever you're doing in the normal dynamic programming algorithm, right? You went to all its neighbors and look, but now you also, what did you do? You went through each of the set, and if they contained Vj, you discarded those sets. So from F1 stupid, let's make an F1 nice. Still, or make F1. What is F1? Is basically, it's a subset of F1 stupid, and what is this? Discard all sets that contain Vj from here, right? This is what we did even in a normal dynamic programming algorithm. What did we say? Okay, let's took the union of all these sets, and if a set contains Vj, let's drop those sets. So this is what we did here. Now we need to show something very interesting. What we can show at this point is basically the set which you have made is Q representative of this. If I can show that F1 which I have made now, okay, so now what you are able to show, this is not very hard, I will show to you, it is K minus I representative of Fivj. If I'm able to show this, then I'm very happy, because what is the size of F1? It is n times, what is the size of n? What is the size of Fi minus? It is going to be n times K minus 1 into, K into I minus 1. This is it. Because whatever I have stored previously has size K, choose I minus 1, because I have kept the representative. Now, whatever I'm giving you as what I'm calling F1 has size at most n into K minus 1 choose I, because it might be a union of, it has n neighbors, but this is what it is. Size of F1. Cardinality of F1 is less than equal to this. Agreed? So suppose if I'm able to prove to you that this is indeed this representative, then I'm very happy. I will apply this algorithm on F1. Right? Now if I apply this algorithm on this one, I get something smaller and I store. So, and this transitivity will tell me that whatever I have stored is actually a representative of whatever you wanted to store. So all I need to show is that whatever F1, this slightly larger set I have constructed, actually represents this correctly. And why it will not? Let's try to, okay, what did I do? Look at here, right? Look at, so what did it say? Look, so for example, at this stage, what it says, so suppose I'm looking at its neighbors, look at all the path which contains Vj. Okay? This is my Vj. And this has size k minus I plus 1. Yeah. No, k minus I plus 1. Because it is I minus 1. Now, look at all the paths which comes from his neighbor, some particular neighbor, say u. Like some particular entry here, some neighbor u. Right? Some neighbor, say v. Here, this set. What is the property of that set? What is the property of that set? For any of this where u comes, it has one set which is disjoint from all this, for each of them. Now, if I include this, for each of them, what am I doing? For each of them, I'm including this Vj as a track. This clearly is, I can, if you give me this as a future, which is one side is smaller, I will be able to handle this. Because it's like a brute force, like all possible ways which I can extend this. This is what F1 is, all possible ways to extend. I mean, there are no other ways. This is all that I'm trying to do at this point of time. So clearly, whatever comes for the future, I will be able to handle it. But what is the clever part at this point of time? So when I am small, I compute larger representative for the larger set. As I go closer, I start to compute representative for smaller set. Yes, please tell me. You look very surprised. Yes.
F contains sets. Yes.
This set, this F.
For our algorithm, we need to consider paths.
Yes.
Why don't we lose some information when we reduce our family?
Because what family you are considering? Whatever you have current family, all of them realizes paths. Look, V neighborhood of this. So you're starting from a single vertex, all the neighborhoods. So it means there is an edge. So this relationship, actually, because I'm only going over its neighborhood, I'm able to maintain that whatever sets I have, they all are valid paths.
Why couldn't it happen that when we have big family, we pick next vertex and we look, there are some paths that have endpoint adjacent to our new vertex.
Yes.
And when we reduce our family, why couldn't it happen that we throw away all paths that has endpoint adjacent to new vertex?
I still don't get it. Okay, so let's, so suppose our new vertex is Vj. Our new vertex, which I'm trying to construct at ith level, at this point, suppose this is a level, right? I want to construct. So this vertex is Vj. What did I say? What is my F1 stupid? What did I say? Look at all V which is in the neighborhood of Vj. Neighborhood of Vj, right? So here I have Vj and I look at all its neighbors. Right? And what did I do? I said, suppose by induction hypothesis, all this contains valid path. Suppose this is a neighbor U1, U2, some UL. Suppose by induction hypothesis, it contains all valid paths, like each set here contains all valid paths of length I minus 1, which ends at U1. Okay? Or it contains a representative of all valid paths of length I minus 1, which ends at U1. This, right? So now what did I do in F1 stupid? I said,
we have family for every vertex.
Yes, union over this, right? It's union over V. This is why we make a very big family. First we made a stupid family by taking stupidly all the union. Then we made F1 by discarding all those sets which contain Vj, delete them. Now I am saying this set correctly represents.
For every family, we remember the endpoint.
Yes. Because this is what, remember what it tells you. Here it stores all the, it's a representative for all paths of length 2 which ends at Vj.
Yeah, probably this picture is slightly confusing.
Okay.
So at the first step, we have
singletons.
Family that upper bound is k choose 1, but actually
it is singleton.
Size is 1.
Yes.
Okay. Now it's clear.
Now is it clear? More clear than before? It could be very confusing because I found it very confusing for a few days before I really understood what is happening. Look, these which I told you, it's slightly, this is why I say it's a slightly non-conventional way of doing DP. So basically, if you think of doing dynamic programming, that I have lots of sets, can I delete some redundancy from this? So this is a way to remove redundancy. Okay? So this is what you do. So basically what happens, at every stage you expand. You make F1, and now you run my algorithm and you shrink. You again expand, shrink. So basically, what is the running time of this algorithm? At any point of time, you do not have more sets than 2 power k dot n. You never have sets more than 2 power k dot n. And to do that, the worst case of p power q is some k power k. So this algorithm will actually run in some k power k poly in n. Okay, please tell me, please ask questions, because I try my best to explain to you. It might be slightly harder, easier. If you ask me question, it might be more clearer for you.
So how do you get this to the k?
That's a set. At the last stage, in the worst case, you can have 2 power k dot n sets, because it should not be 2 power k dot n. This is not correct actually. It should be like k choose 1 dot n, because it is k choose k minus 1, right?
Right.
Lastly, it will be k choose k minus 1, which is nothing but k choose 1. Like here for k minus 1, what is the size of this set? It's k choose k minus 1, which is nothing but k choose 1. So basically the bad thing is when it becomes k by 2. It is k choose k by 2, which is like 2 power k.
So for the last column, the size is small, but the worst column has size
k by 2.
To the k.
Yeah, because k choose k by 2, right? In the beginning, it's all small, 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 small. Like k choose 2, k choose 3, k choose 4. When it hits I equal to k by 2, it is k choose k by 2, which is like 2 power k. And so, okay, so this is how you do this. I mean, I try to give you a full, complete algorithm for k path. Of course, modulo. So this DP algorithm remains the same. What will change is how fast, given this family, I can compute its representative. Mm-hmm. Right? So the basic core of the algorithm is this. And fortunately or unfortunately, this is the only way I have seen how this DP is used. So you go, you expand. So basically, you are trying to compute representative of a very big family which you don't see, which is very, okay? So at each step, you make slightly bigger family, which is still FPT, you shrink, you again do the next step, you make it big, you shrink. So at each step, you keep reducing it. And at each stage, you keep using this, what you call, transitivity to show that whatever you have is nice and good, because each time you're trying to compute representative of really a very big family. Mm-hmm. And we cannot give this to my algorithm, because then we are dead and dumped. So all the time we make slightly bigger, smaller, slightly bigger, smaller, bigger, smaller. How to shrink? So I have this family F1. I apply my algorithm, right? I had an algorithm which you give him a family of size t, right? In p power q times t square, it gives me this smaller family, this branching algorithm, this much time. So this is why, what is the worst case for p is k, what is the worst case of q is k, so it is k power k, and what is the worst case of n? It is 2 power k dot n whole square. So basically this algorithm is going to run, in k power k, 4 power k, some n square. Is it true? Yeah, it's true. Something like that. But this is one stupid algorithm. There are much faster implementation of these things.
Well, but in our case, p plus q is always k, right?
Yes.
Okay, so k to the k is like overestimation.
Yeah, it's an overestimation. But you put p equal to k by 2, and then we are dead.
Yeah.
But something very beautiful happened. Okay, this is something which I would like to notice. Although the running time is bad, but what are you storing in your DP table? It's something which is not more than 2 power k ever. So space wise, it is some 2 power k dot poly in n. This is all that you are storing here, right? Storage. So what is hard is to how to compute these sets efficiently that we can meet this. So if suppose suppose we had an algorithm which ran in time big O of t. Suppose if we had an algorithm which did not depend on P, did not depend on Q, then what is the running time of this algorithm?
Say it again.
Suppose we had an algorithm which you give him a family of size t in big O of t time, in linear in the size, it is able to output my smaller family. Then what will be the running time of this algorithm?
N square.
4 to the k or 2 to the
No. Now we have big O of t algorithm, right?
right, but we still need to.
No.
Oh, right. So just 2 to the k.
Then the algorithm will have running time 2 to the power k dot n square. Now two things in order. Okay, for k path.
But we don't know such.
With?
We don't know such.
We don't know yet. But roughly we know how to do this in, I would say, okay? And that is what gives us, roughly, this is not correct to state in this way, but roughly this is what happens and this is what gives you.
So roughly is 3 to the k. No, 2 to the.
Roughly it is 2.85 to the power k, but you can use this algorithm in even much more smarter way. And you can get an algorithm for deterministic running time, which is 2.618 to the power k. Okay, but there are 2 points to make. Okay, now this algorithm not only will work for k path, but if you're looking for, you're given a graph of k size tree, and I'm asking, does this k size tree exist as a subgraph, like as a generalization, k path, right? For that, using Seth, strong exponential time hypothesis, we can show that you cannot have this algorithm. So k path is exception that you can go better than 2 power k. For k tree, you cannot. You cannot have 1.999 to the power k algorithm. So this algorithm can also make work for trees, graphs of bounded tree width, and blah blah blah. So this approach, we cannot make this approach deterministic and go below 2 power k. Maybe we need some other machinery. But the best hope is that if we are able to compute a linear time algorithm for this, which is a open problem, so this is your first open problem, given this family, how to compute this in linear time. I think it's a very nice, beautiful open problem, according to me. And it is possible that we might have, because there's no hindrances for this. And even Ryan Williams think that there should be some linear time algorithm for this. So if he thinks, he believes.
What do you mean even Ryan?
He heard the talk and he thinks that it has a linear time algorithm.
Yeah, but he believes that ACTH is wrong, if I remember correctly.
Yes. So, but till then we just believe on the positive side and we are happy. No, but this algorithm, this P plus Q choose P, which I showed you, is a tight lower bound. We cannot do better. You need this much sets. Okay? For example, if you had very good, very simple example. You take universe of size 1 to P plus Q. Okay? And your family is all sets of size P. What is the size of this family? K choose P. Or P plus Q choose P. Right? Now for any set, its disjoint is unique. So you need every set. So this is actually tight. You cannot improve this from P plus Q choose P to anything. And so this is somehow implicit. So this is a very simple example which tells you that these bounds are tight actually. So at least in terms of space, we can never go below this. But if we can compute, we will have the fastest deterministic algorithm. Okay? Okay. Everyone looks very tired. What's the time? It's 5, roughly 4:45.
Why is the last one is 2 to the k?
It's not 2 per k. It should be k choose 1. It should be k choose 1.
Okay.
Yes. It's stupid. It's k choose k, which is not 2 power k. It says k choose 0, which is 1.
At least it is less than 2 to the k.
It is less than 2 power k. Okay. So this is how you can do dynamic programming algorithm. Okay. Okay. So what I want to do after this, we did a vertex cover kernel, right? Vertex cover kernel. let's do a vertex core kernel using this idea, just for like some kernel. And then if you still have energy, I can try to tell you an algorithm to do this, which is very fast. And that is a little bit of linear algebra. It is a bit of linear algebra. But all you need is what is determinant, and I will not bore you with Matroid. Finally, I planned to say that this is what Matroid is, but I wouldn't bore you with that. So let's take a break. Let's see at least one more why to see more application. And if you still have energy, you tell me, whoever has, we can try to see. It will not take much time, but it's not very straightforward. You need to understand few things here and there. It is a very nice, according to me, it's a very nice, once you get the idea, the proof is not very hard. But I think this idea is slightly non-trivial, to get this algorithm.